Every day we see objects resting on inclined planes. Depending on the object, the surface, and the inclination angle, it will be easier or harder for this object to slip down the incline. Let's look at the specific case of a car parked on an uphill street with an angle theta. Drawing a free body diagram of the car, we need to define distances. Let's call d sub cg the perpendicular distance between the ground and the center of gravity of the car, d sub f the distance between the front tire and the center of gravity, and d sub r the distance between the rear tire and the center of gravity. From our force diagram, we see the weight needs to be cancelled out by the reaction forces on the front and rear tires. These reaction forces, however, can each be decomposed into two components, a component normal to the plane and another component along the plane. From now on, we will refer to the normal component as the normal force N, to the component along the plane as the friction force lowercase f. To make our calculations easier, we will align our x-axis with the inclined plane. Our equilibrium equations, as always, are sum of forces in x equals 0, sum of forces in y equals 0, and sum of moments about any given point equals 0. Along the x-axis, we have the two friction forces and the negative horizontal component of the weight, which equals the weight times the sine of theta. Along the y-axis, we have the two normal forces and the negative vertical component of the weight, which equals the weight times the cosine of theta. If we take our sum of moments about the contact point of the rear tire and take counterclockwise rotations as positive, we have a negative moment from the vertical component of the weight times d sub r, a positive moment from the horizontal component of the weight times d sub cg, and a positive moment from the normal force at the front tire times d sub r plus d sub f. Both friction forces and the rear normal force have lines of actions that intersect the point about which we are taking our moments. Thus, they create no moment. Our equilibrium conditions yield the following equations. Solving for the normal force on the front tire from the moment balance equation, then substituting this in the y-axis force equilibrium equation to solve for the rear normal force, we arrive at the relationship between normal forces and friction forces. From physics, you know that the friction force equals the normal force times a constant called mu, also known as the friction coefficient. Mu depends on the material of both the body and the surface. A high friction coefficient corresponds to high friction between the body and a surface. There are two types of friction coefficients, static and dynamic. You should use the static friction coefficient whenever an object is not moving. If the force acting to move the object becomes larger than the maximum allowed friction force, the object will begin to slip. Then, if the object is slipping over the surface, you should switch to the dynamic friction coefficient in your analysis. Substitute the previous equations we solved for n sub r and m sub f into the friction expression. Plug in everything into our x-axis force balance equation and arrive at the conclusion that the static friction coefficient equals the tangent of theta, the inclination angle. For our specific example, a parked car, the value of static mu for a rubber tire on dry concrete is 1. This means that the maximum inclination before our car starts to slip on dry concrete is 45 degrees. Any angle steeper than 45 degrees will result in a static friction coefficient larger than 1 to keep the car in equilibrium. However, if the concrete is wet, the static friction coefficient is 0.3 only. The maximum inclination angle before slipping occurs, in this case, is 16.7 degrees. You definitely do not want to drive up steep hills when it's raining.